Welcome back to Math 332. Before we look at the solutions of our first exam, I think this is a good time to look back at the important ideas that we have learned prior to exam 1 and what are the things that we are going to study in the following weeks. We started the course by looking at a system of linear equations like this and learn how to put the systems into an augmented matrix and how to row reduce it to REF form. And once we have the system in REF form, we can tell what are the solutions easily. For example, in this case, x, y, z are simply 1, 2, and 3 respectively. Some systems has free variables and hence has infinitely many solutions, like the one that we have here, where the pivots are the x1, x3, and x5. The free variables are the x2 and the x4. And if we set x2 and x4 to be t and s respectively, then we have the general solution of the systems that looks like this. So these techniques of solving system of linear equations is something that you must have mastered prior to the first exam. And you will see that we are going to continue to use this concepts idea to solve problems that is a little bit more abstract, but eventually will reduce to a system of equation like this. In fact, you will start seeing problem like that in your homework number 5. So also in this course, I assume that you already know matrix operations like additions, subtractions, both the scalar and matrix multiplications. And you should also know that the matrix multiplications are not commutative. That is to say that for matrices, A times B might not be equals to B times A. Most of you know that, but you also have to be aware that matrix multiplications are not the same as like multiplying real numbers. So for multiplying real numbers, if you have a squared equal to 0 for real numbers, then your a has to be 0. But this is not true for matrices. For example, if you look at this case, a 2 by 2 matrix, where this is matrix A is clearly not 0, we have 0, 1, 0, 0. Yet, if you compute A squared, you can see that A squared is actually a 0 matrix. So this tells us that A squared equals to a 0 matrix doesn't imply that A equals to 0. This is one of the common things, mistakes that you make in the exam, which a lot of you guys claims that A squared equal to 0 will implies A equal to 0. Now you have to know that that is only true for real numbers and it's not true for matrices. So you should be aware of the differences between matrix multiplications and multiplications between numbers. So moving on, we also spent time studying the concept of determinant. We learned how to compute the determinant of a matrix by doing a cofactor expansions. We also study its various properties, but the most important things that you need to know is that we are going to use the determinant basically to tell whether or not a square matrix is invertible. That is the theorems given here, 2.3.3, which says that a matrix A is invertible if and only if the determinant is not equal to 0. We will use this important theorem many times in this course, so please be aware on the statements of the theorem and how do you use it. After this, we started to look at another aspect of linear algebra, and things started to get a little bit more crazy, a little bit more abstract. What happened is that we know how vectors in Rn works. I mean, that is a concept that's very familiar to basically all of us. For vectors in Rn, for example, these are typical vectors. This is the first thing that when you learn about vectors, you know vectors looks like this, and this is how we can add vectors, and this is how we can multiply vectors with a scalar. But we have also seen that many other systems also have such properties which are pretty similar. For example, if you look at the matrix, the spaces of 2 by 2 matrices, we can also add matrices together. We can also multiply matrix with a scalar like this. Not only that, say for example in spaces of polynomial, in this case polynomial of degree at most 2, you can also add polynomials together like this. We can also multiply a polynomial with a scalar. So they are very similar. Also, one more example here is that the space consists of all the functions defined on a real line. We can also add the components in that space like this, and we can also scalar multiply the functions in that space like this. So instead of looking at all these examples separately, mathematicians put all these objects into one single framework, which we call vector space. In fact, we have kind of already verified that this 2x2 matrices, if you have addition operation and scalar multiplication defined like this, then all the axioms for vector space will check out. They satisfy all the axioms of vector space. This is why we call them vector spaces. So the meaning is basically says that if it satisfies all the axioms for vector spaces, then all this thing kind of just behave like the usual Rn, usual vectors that we know. So in the coming weeks, we are going to learn how to study the concept of expand, basis, dimension, and so on for our regular vectors in Rn. And we want to extend all those basic concepts in Rn to spaces like M2x2, P2, or this function space. So things are going to get a little bit more abstract, but it wasn't so bad. I want you to kind of like stop making a conceptual mistake like some of you have shown in the exam, which we are going to discuss in our second videos immediately following this. So see you in the second video.